All right, advanced geometry. This is Monday, March. Yeah, it'll be Monday, March 5th notes. It's the beginning of chapter 8. It's kind of interesting. This first section usually is a breeze, and we go on to the next section, and that's where it gets harder. I would say this section just starts in a little bit odd. It's not maybe as intuitive as some of the first sections of the chapters usually are. So here's chapter 8, section 8.1. All right, we're still going to be dealing with triangles in this chapter. We talked a lot about similarity last chapter. That was the entire chapter. Okay, so shapes that weren't necessarily the same size, right? But they were the same shape. Now we're going to be within one triangle. So we're going back to right triangles, things that we can find, similarities that exist within one triangle. So that's where we're picking up chapter 8. Still talking about similarity, but it's within one triangle now. And then there's also another word, a new phrase you're going to learn. It's the geometric mean. All right, the geometric mean is something you haven't seen before, a lot like everything in chapter 8. Chapter 8's just got a lot of new stuff in it. The geometric mean is simply a situation where A over X is equal to X over B. So the key is that that number is consistent. So the lower left and the upper right number have to be the exact same value. This is your geometric mean. This value of X then is the geometric mean of the two numbers of A and B. Okay, so it's, when you think about the average, usually that's what mean is. Okay, when you think about the average of two numbers, you add them and divide by 2. Well, this is the geometric mean, or average, I guess you could say, of two numbers. These values, the A and the B, are oftentimes called extremes. So the A and the B values are the extremes, and then this value of X is your geometric mean. Okay, so let's see an example of that. We're going to find the geometric mean of 6 and 15. So find geometric mean of 6 and 15. All right, now 6 and 15 are your extremes then, okay? Those will go in the outs, they're like the far, is how I think of it, the upper left and the lower right. I guess I think of this as box 1, box 2, 3, and 4, so it kind of makes sense in my head that way, but I know everybody's a little different with that understanding. Sorry for the glare. All right, anyway, the key is that 6 and 15 go in the extreme location, and now you solve using cross products. So you end up getting x squared is equal to 90. 6 times 15 is 90. And then to get the geometric mean, you square root 90. This is going to take you back to simplifying square roots, and it is absolutely important that you do. You can't do decimals. I don't want decimals. I want simplified radical form. So that's another kind of mountain that some of you might have to climb up this chapter. So if I wanted to reduce the square root of 90, I'm going to go ahead and, first of all, put plus or minus, because there will be 2 answers. And then I want to go ahead and do square root of 9 times 10. Square root of 9 is 3. So 3 square roots of 10 is my geometric mean. Now, given the fact that I have 2 positive values, it doesn't make sense that 3 square roots of 10, the negative answer of 3 square roots of 10 would really make much sense. So in fact, the actual answer for this is just the positive root, because a negative value would not make sense for this case. All right, that's what a geometric mean is. Again, it'll be a kind of interesting thing for you until you get used to it. There are 2 theorems that are a part of this section that come from similarities within a right triangle. So let me try to set this up for you. Let me do this the other way so it's maybe a little easier. So if you have a right triangle to start with, so one 90-degree angle, I'm going to have that be this one up here. So this is my 90-degree angle, okay? And then I draw from the 90-degree angle the altitude. So the altitude creates 90-degree triangles then within it. So I have a series of 3 90-degree triangles. So let's call this big one A.
Malachi Burgess, please report to Mr. Post's room before you leave. Thank you.
C. And we'll give this guy, we'll call this guy Z. All of within these triangles, you have 3 similar shapes, which is kind of interesting. That you can have the big triangle be a similar shape to this right triangle that I'd say is the medium-sized triangle over here, the right side, is similar to the left side. So there are 3 different shapes in here. So I'm going to go ahead and try to highlight that and show you. So you've got the big one. You've got the one that's kind of medium, the middle one. And then you've got this little one over here. And they are all similar to each other. So if you kind of wanted to set them up, so I'm going to go ahead and try. So AB is the short base of this. I don't know if you'll be able to see this or if this will make sense right off the bat. I'll try to color code it. But I'm trying to take the blue triangle now and flip it so it's on its base. So the B, hey, I'm in the middle of our notes class on Monday.
Can I interrupt?
Yeah, go for it, but everybody's going to hear it.
Okay, that's okay. Did you post the review answers for the test?
Okay, there.
Awesome. Thank you.
Yep, good luck studying.
Hi, class.
Thanks, Abby. Okay, so the B, A, and C, this is the blue triangle, is in fact similar. And if you can kind of tilt the pink one, then.
Sean Vandenberg
So
to
Z,
the attendance office.
B, and then its top is C. Z is at the right angle, and then B is here. That's the pink set. Followed by the yellow. Can't see that, can you? Sorry. Okay, and then followed by the yellow one. So I'm going to also set that up. And have its short side be AZ. The Z. This is A. And B. So the reason I tried to position them this way is so that you can see which sides actually correspond to which sides. This is a puzzle, one that I can't necessarily see every time, but some of you may be better at it than I am. So side ZC, you can see me over here. This side is going to correspond to the blue BC side, and the BC side is going to correspond to the yellow's BZ side. I mean, it's all sorts of twisted around. So if you want to figure out which side corresponds with which side, which angle matches with which angle, it's a little bit complicated. But because these 3 shapes are all similar, these triangles are all similar, they're all proportionate in sides and all their angles are congruent, you can come up with 2 really cool theorems. There are the altitude and the leg theorem, okay? The altitude and the leg theorem. So the altitude theorem will be first, and the leg theorem will be second. Now, I've watched this YouTube video that I'm not going to be able to show you, but the YouTube video has kind of a cute way to remember it. So let me show you what it looks like first, and then I'll explain. So I've got this setup each time. It'll be very similar, where you have a right triangle kind of positioned this way with an altitude drawn. Okay. And then, for example, I'm going to label this with 2, X, and 8. All right. So the altitude theorem says this. It says there's a proportion, the geometric mean, actually a better word for it now that we know that. The geometric mean of the 2 pieces of the hypotenuse is X. So in other words, it looks like this. 2 over X equals X over 8. The geometric mean, the altitude, is the geometric mean of the 2 pieces of the big hypotenuse. And again, the whole reason it works is because of the way that these sides are all proportionate. It comes out of the similar shapes. And I'm guessing that's going over your head because I haven't really broken it down well enough for you. But for people that are curious about it, you could figure it out. This is just a simple proportion based on similar shapes. All right, so here's it's called the heartbeat. Heartbeat theorem, because you know those heartbeat monitors that you see in the hospitals. I guess that's timely, right? That's what we'll all be looking at for the next week. Those ones that go beep, and beeps are good because it means you're alive. Okay, anyway, that's what this does. You watch. You go from the 2 up to the altitude, so 2 over x, down the altitude, so x, across the base, 8. I'll try to find that YouTube video and throw it on to PowerSchool as well. So that's the altitude theorem. You're going to use that to solve. And so I could do that here. I could get x squared is equal to 16. X is equal to plus or minus 4. But we all know negative 4 can't be a side length. So I just leave it as 4. All right. The leg theorem. Exact same setup. So you're going to have to get used to doing that one more time. Sorry, guys. These are longer notes today. Hopefully. What am I at, 11 minutes already? Yeah, sorry about that. Hang in there with me, almost done. The leg theorem means the leg of the big triangle, so we're thinking the blue triangle, which this blue triangle is what I'm referring to. Think about the blue triangle, the outside triangle, as the leg, and then it looks something like this. So the leg is the geometric mean of the blue triangle's hypotenuse and then the short side of the hypotenuse that touches the leg. This is such a tricky section to teach in video notes. But that YouTube video that you'll watch, this is called the boomerang because it makes a boomerang. I don't know how to spell that, so we're going with the boom. So watch what it does. So you start across the hypotenuse. So I go hypotenuse, up the leg, back down the leg, and then you just go halfway. So here's what I mean by that. I start here. I go along the hypotenuse, so I write 24 down. Then I go up the leg, which would be x, equals back down the leg. Oh, not x, it's 10, isn't it? Sorry about that. 10, up the leg, which is 10, back down the leg, which is 10, and across the remaining part of the hypotenuse, which is x. So the leg is the geometric mean of the hypotenuse and the part of the hypotenuse that touches the leg. Okay, 24x equals 100. X is going to equal 4.16, approximately. I don't know if that was a rounded answer or not. All right, let me see if I have any more examples. Listen, I know that's a lot. One more hint before I cut you off. Don't forget that Pythagorean's theorem is always an option. So if Pythagorean's theorem exists within a right triangle, use it. That's a safety net. That's a way to go about solving this. Mr. Hansen on Wednesday should know a lot more about it if you're stuck then before the quiz, but it's only one part of the quiz. So good luck. Help each other out, please. I know it's a lot. Do the best you can. Practice the homework. Do the homework. Thanks, guys.